this video, we will learn about op-amp Wien Bridge Oscillator. Op-amp Wien Bridge Oscillator. This one is op-amp and lead lag network. This op-amp is in non-inverting configuration. This one is lag network. Lag network means R and C are connected in series. This is lag network. And this one is a lead network. This one is lead network. The lag and the lead network acts as a feedback network for this Wien Bridge Oscillator. The lag and lead network introduces lag and lead network. Lag and lead network introduces 0 degrees phase shift. Introduces 0 degrees phase shift. Op-amp is in non-inverting amplifier configuration. Gain of the op-amp is 1 plus RF by R1. This one is RF. This one is RF. Non-inverting op-amp amplifier configuration introduces 0 degrees phase shift. Non-inverting op-amp amplifier introduces 0 degrees phase shift. For total phase shift around the loop, total phase shift around the loop. Around the loop is 0 degrees. 0 degrees plus 0 degrees is that is equal to 0 degrees. Barkhausen criteria condition is satisfied. Another condition is A beta mod A beta greater than or equal to unity, where A is the gain of the operational amplifier, beta is the feedback factor of that network, lead lag network or lag lead network. This is the op-amp. Op-amp is in non-inverting amplifier configuration because output of the amplifier, non-inverting amplifier, is fed back to that non-inverting terminal of that op-amp. That means plus through this feedback network. This is the feedback network. This is the feedback network. The important points here are the op-amp is in non-inverting amplifier configuration. First point. Second point, lag lead network or lead lag network acts as a feedback network. It introduces 0 degrees phase shift. Op-amp in non-inverting amplifier introduces 0 degrees phase shift. Total phase shift around the loop is 0 degrees plus 0 degrees is equal to 0 degrees. Small a beta is greater than or equal to 1. These two conditions are satisfied, then only the Wien Bridge Oscillator produces pure sine wave. This is the output. Calculate time period of the waveform T. The frequency of oscillations of T is equal to 1 beta. Next, coming to this is the lead lag lead network. Generally, this one is output of the, this one is frequency, phase. At this frequency, for lower values of frequency, this is the resonance frequency FR. For lower resonance frequency FR, for lower frequencies, that means F less than FR. This is the frequency range. The phase shift introduced by the lead lag network is advance. that is advanced phase shift. And F is greater than FR, that is the delayed phase shift, advanced phase shift and some delayed phase shift. At F equal to FR, the phase shift introduced is 0 degrees. Therefore, totally lead lag network introduces 0 degrees phase advance and phase delay. At resonance frequency, the output is very high. The output is that lead lag network is very high. This is the characteristics of the lead lag network. This one, RF and R1 is particularly suitable for gain calculations. This is the RC and RC, series RC and parallel RC, particularly is called as lead lag network. It introduces 0 degrees phase shift. The gain of that op-amp is controlled by using these two resistances, RF1, R1, RF1, R1. Here, the intersection point here, R and C are connected in series, R and C are connected in parallel. The intersection point is connected to positive terminal of the op-amp, that is a non-inverting terminal of the op-amp. Therefore, that introduction point, CR and RC, the intersection point is D. This is connected to positive terminal of the op-amp. Here, C, lag network C is connected to output. Lag network C is connected to output, that is in the series arm. Lag network C is connected to output. Next one, this is the R and C parallel network is connected to ground. R and C parallel network is connected to ground. These are the elements. Non-inverting terminal, inverting terminal of the op-amp is connected to junction of R1 and RF. Inverting terminal of op-amp is connected to junction of RF and R1, RF and R1. Another end of that RF is connected to V0. Another end of RF is connected to V0. This is the V0, another end of RF, that is junction of C and RF. That is the junction of, this is the C, and another end of RF is connected to output. This is the C, and another end of RF is connected to ground. R1 and RF is connected to, junction is connected to inverting terminal of the op-amp. Advantages and disadvantages. Mounting the two capacitors on common shaft and varying their values. The frequency can be varied as per the requirements. These two capacitors are mounting on common shaft and varying their values easily. The frequency can be varied as per the requirement. Due to use of here not two stage, due to use of non-inverting op-amp configuration. Non-inverting op-amp configuration. Gain A is equal to 1 plus RF by R1, provides high gain. Stability is high. It provides stable load distortion. Sinusoidal output, pure sine wave is obtained. The frequency range can be selected simply by using decayed resistance boxes R and R. The circuit is easy from design point of view and gives the constant out. Disadvantages. It cannot be used to generate high frequencies. It is used to generate audio frequency range. The circuits, in case of transistors, we use needs 2 transistors and a large number of other components. In case of op-amp, the complexity is eliminated. The maximum frequency is limited due to the amplitude and phase shift characteristics of the amplifier. These are the advantages and disadvantages of the Wien Bridge Oscillator. Frequency and gain derivations of the Wien Bridge Oscillator. Frequency and gain derivations of the Wien Bridge Oscillator. Wien Bridge Oscillator. Here, this is the output is connected to input of the network, and output of that this lead network is connected to positive terminal of that op amp. Positive terminal of that op amp. By using this one, draw this one. Here we use instead of R and C, we use R1 C1, R1 C1. This one is R2 C2. This is the output of the op amp configuration. This one is the output of the op amp configuration. V0. Output of the op amp configuration is V0 is connected here. Here, this one is VF. This one is VF. This one is VF. Output of the feedback network. This is the op amp gain A. This is the feedback network, lead lag network. This one is output. Output of the amplifier network is V0. Output of the feedback network is VF. Like that. In that fashion, I have to connect this one. Series combination can be treated as Z1. The parallel combination is treated as Z2. Find out beta. First find out beta value and then find out mod A beta greater than or equal to unity. We know that beta is equal to VF by V0. Output of that feedback network by input to the feedback network, that is V0. From this one, output of that amplifier is V0. Output of that feedback network is VF. According to voltage division rule, VF is equal to total voltage applied to the circuit is V0 into Z2 by Z1 plus Z2. Therefore, beta is equal to, we know that VF by V0 is equal to Z2 by Z1 plus Z2. Z2 by Z1 plus Z2. Here, Z1 is equal to, we know that these two are connected in parallel, R1 plus J omega C1. Z1 is equal to R1 plus J omega C1. These two are connected in series 1 by J omega. Capacitor reactance is equal to 1 by J omega C1. 1 by J omega C1. That is equal to R1 minus J X. Jx, where X is equal to 1 by omega C1. Here R1 plus 1 by J into X. This one is R1 plus 1 by j. 1 by omega c1 is equal to x. Numerator and the denominator. This one is r1. Numerator and denominator is multiplied with j. J into j, j square. J into j, j square. J square means minus j x. Therefore, z1 is equal to r1 minus jx. z2 is equal to r2 into 1 by j omega c2. 1 by j omega c2 plus by r2 plus 1 by j omega c2. R2 into 1 by j omega c2, r1 by r2 plus 1 by j omega c2. That x1 is equal to 1 by omega c2. That is equal to z2 is equal to r2 j numerator and denominator is multiplied by j. J here j square. J square is minus, that is the minus j r2 minus j x1 r2. Here numerator and denominator is multiplied by j. J square is minus j 1 by omega c2 is x1. Therefore, z2 is equal to minus j x1 r2 by r2 minus jx. Therefore, z1 is equal to r1 minus jx. z1 is equal to r1 minus jx, and z2 is equal to minus jx1 r2 by r2 minus jx1. By using these two equations, beta is equal to z2 by z1 plus z2. z2 is equal to this expression minus j x1 r2 by r2 minus jx1 by z1 is here, z1 is r1 minus jx. z1 is r1 minus jx. z2 is here, z2 is minus jx1, this one minus jx1 r2 by r2 minus jx. That is equal to minus j x1 r2 by r1 minus jx r2 minus jx r1 minus jx and r2 minus jx minus j x1 r2. Simplify this one. This r2 minus jx1, r2 minus jx1 is cancelled after multiplying r1 minus jx with r2 minus jx1. That is equal to minus j x1 r2 by r1 r2 minus j x1 r2 minus j r1 r2 minus j x1 r1 here x1 next minus j x r2 j into j square, that is minus into minus plus minus x x1 minus j x1 r2. That is equal to minus j x1 r2 r1 r2 minus R1 R2 minus x1. This one is minus j into x1 R1 plus x R2 plus x1 R2. This is the beta. Generally, beta is the feedback factor. Lead lag network introduces lead lag network introduces 0 degrees phase shift. 0 degrees phase shift. Introduces 0 degrees phase shift means the quotient of the J term is 0. That is the quotient of J term is 0. 1 R1 plus XR2 1 R2. One more correction here is the numerator and the denominator is multiplied with the J term. Entire term. After that only that is equal to J is equal to 0. J into J square minus into minus plus. That is x1 R2. This is the J term. J into R1 R2 minus x1. This one is J square. This one is J square. J square is minus 1 minus into minus plus x1 R1 R1 plus xr2 plus x1 R2 x1 R2. The J quotient value is equal to 0 means R1 R2 minus x1 is equal to 0. R1 R2 is equal to x into x1. We know that x is equal to 1 by omega c1. x1 is equal to 1 by omega c2. That is equal to R1 R2 is equal to x is 1 by omega c1. x1 is equal to 1 by omega c2. R1 R2 is equal to 1 by omega square c1 c2. Omega square is equal to 1 by R1 R2 c1 c2. That is equal to omega is equal to 1 by square root of R1 R2 c1 c2. Omega is equal to 2 pi f square root of R1 R2 c1 c2. We know that f is in a Wien Bridge oscillator. R1 is equal to R2 is equal to R. C1 is equal to C2 is equal to C. F is equal to 1 by 2 pi R square C square. That is equal to F is equal to frequency of oscillations of the Wien Bridge oscillator is 1 by 2 pi R. This is the Wien Bridge oscillator frequency. Coming to this one, the J quotient is 0. Therefore, beta, the remaining beta is equal to x1 R2 by x1 R1 x R2 x1 R2. Therefore, the remaining beta is equal to x1 R2 by x1 R1 plus x R2 plus x1 R2. Okay, next A beta is greater than or equal to unity. First, we have to find out the beta value. We know that x1 is equal to 1 by omega C2. R2 by omega C2. X1 is equal to 1 by omega C2. That means R1 by omega C2. X is equal to 1 by omega C1. R2 by omega C1. X1 is equal to 1 by omega C2. That is equal to R2 by omega C2. In all the cases, omega, and omega is cancelled. Therefore, finally, beta is equal to R2 by C2, R2 by C2, here C1, C2, R1, C1, R2, C2, R2, C1. C2 is cancelled. C2 is cancelled. Finally, that is equal to R2, C1 by R1, C1 plus R2, C2 plus R2, C1. This is the beta. But in case of Wien Bridge oscillator, R1 is equal to R2 is equal to R, C1 is equal to C2 is equal to C. Therefore, beta is equal to RC by 3RC. Therefore, beta is 1 by 3. But mod A beta greater than or equal to 1. Therefore, mod A greater than or equal to 1 by beta. Mod A greater than or equal to 1 by 3. Therefore, mod A greater than or equal to 3. The gain of the Wien Bridge oscillator for producing sustained oscillations, the gain of the Wien Bridge oscillator is mod A greater than or equal to mod A greater than or equal to 3. We know that gain of that feedback inverting op amp used in Wien Bridge oscillator is 1 plus RF by R1. Here mod A is equal to 3, 1 plus RF by R1. Therefore, RF by R1 is equal to 2. The value of feedback, pairing feedback, suppose RF is equal to R1. RF value set to such that the value of RFN is equal to R1. With this, the derivation of that gain and the frequency of the Wien Bridge oscillator is completed.